Here's an example of an arrangement that it's on its face looks like a permutation, but may not. In the end, really doesn't make sense to be a permutation. We have a pizza company, and it's 5 different toppings to offer. That's how many distinct two-topping pizzas can it make? Meaning, like you wouldn't do pepperoni and more pepperoni. Um, on its face, it looks like it's straightforward, like the previous problems, in that we have 2 choices to make, and there are 5 choices for the first topping and 4 for the second. However, it's not as straightforward as this because it, unless you have an incredibly sensitive palate, you can't tell the difference between which topping went on first and which topping went on second. So, like, maybe to be a little more concrete, if the 2 toppings we'll make this controversial, ham and pineapple. Like, this is the same pizza as pineapple and ham. So even though if ham came first and then pineapple, or pineapple then ham, um, if we counted it like this, that would mean that each of those 2 pizzas are different. But really, they're not. You can't. Again, unless you're really really pizza sensitive, you're not going to be able to tell the difference between those 2. So we need to take account all the ways you can rearrange the toppings that you've chosen, and the number of ways to, if once I've picked 2 toppings, to rearrange them is there are 2 factorial ways to do that. So in the end, what we're going to do is we're going to have to divide by all the ways to arrange the toppings we've chosen, which is 2 times 1 ways, which works out to be 20 over 2, which is 10 pizzas that are distinct. So the idea of combinations takes this into account. Takes into account all the ways that you can arrange everything if you could tell the difference, and then looking at all of the different ways that all the different arrangements that are in fact identical if you don't care what order they came in. So we say that a combination is a selection of objects without regard to order. Without regard to order. All we're looking for is how many ways can we get these things into a group. You may remember some notation for this in the past. This was the number of combinations, NCR. We saw in the previous notes that this is in fact what's called a binomial coefficient, and we can, in the more common notation for this, is n choose r. And using factorial notation, that's n factorial over n minus r factorial times an additional r factorial in the denominator. You might notice this. You might note that this is also the same as the number of permutations divided by r factorial. A bunch of different ways to write the same thing. So if the context of your problem means that there does not matter what order that you're selecting the objects, you just want to see how many ways there are to get groups with the same things in them, then combinations can be the way to go. So here's an example. We have a committee of 4. We're going to choose a committee of size 4, and there are 7 men and 6 women to choose from. I want to know how many different combinations of these committees can we have. So let's see. If there are no restrictions, then let's see. How many people do we have to select from? We have 7 plus 6 is there are 13 people to select from, and we want them to put in groups of size 4, which would be 13 choose 4. You can work this out. Again, this would be the shorthand, kind of the shortcut to remember how to writing these out, is we start at 13 factorial. I'll start at 13, and we're going to do its factorial this many digits. So 13 times 12 times 11 times 10. So there's 4 in a row. And then the denominator is always the bottom factorial. 4 times 3 times 2 times 1. You may note that there's some little bit of simplifying you can do if you need to work this out by hand, which is something you may have to do on like a non-calculator part of a test. 4 times 3 is 12, so the 4 times 3 and the 12 cancel. 2 goes in the 10 5 times, so this is really whatever 13 times 11 times 5 is. And maybe we'll check my calculator. 13 times 11 times 5, which is 715. You could check that on your calculator on an Inspire. That's in Menu, Probability, Combinations, and it's we'll do 13, comma 4, and what do you know? 715. Okay. What if we make some restrictions? What if there must be 2 men and 2 women? So I think the number of ways to do that, since there are 7 men to choose from, we want to put 2 of them into a group. So 7 choose 2. And there are 6 women, and we want to put 2 of them into a group. And then if we take the committees with of all the different combinations of 2 men, and multiply that with all the different combinations of 2 women, we'll get the total number of committees here. And again, if you need to work that out, that'd be 7 times 6 over 2 times 1. And then 6 times 5 over 2 times 1, which would be 21 times 15, which is 315. Note, the more restrictions you put on the committees, the smaller the number will be. So there's definitely less committees of this specific type than there are with no restrictions at all. What happens if there needs to be at least 1 member, 1 man, and at least 1 woman? So I think, what are all the ways you could do that? Well, you could have 2 and 2, but you could also have 1 and 3. You could have 2 and 2. Or you could have 3 and 1. Now, if I think we take all the committees of each of these types and then add them together, we'd know how many committees there are with at least 1 man and 1 woman. So this expression would be, in a non-calculator part, this expression would probably be good enough, unless it says specifically in the instructions to leave your answer as an integer or a whole number. But in any event, I think this would be just fine, although we could work this out maybe real quick. 7 times 1, 7 choose 1 is 7. 6 choose 3 works out to be 6 choose 3 is, let's just use my calculator here. Menu, probability, combinations. 6 choose 3 is 20. We already said that 7 choose 2 times 6 choose 2 is 315. And 7 choose 3 7 choose 3 is 35. 6 choose 1 is 6. So 7 times 20 plus 315 plus 35 times 6 is 665 committees. Okay. An application to counting that's you won't be necessarily tested on in a standardized testing environment, but it's kind of fun example for anyone that plays cards. Are looking at the number of poker hands that are possible in a 5-card game. It's a pretty common thing that a lot of people that are into playing cards like this kind of would like to know. And it's a kind of fun way to try to think about these combination ideas. So so we're on the same page. A 52-card poker deck has ace, 2, 3, jack, 10, jack, queen, and king in it. That's 13 of each denomination. And there are 4 suits. There's hearts, diamonds, spades, and clubs for a grand total of for 52 cards in total. A royal flush is a combination of cards that's ace, king, queen, jack, 10, and all the same suit. So in order to get a royal flush, I think one way to think of getting a royal flush is let's pick what suit is possible. I think there are 4 suits to pick from, and we want to choose any one of those suits to be the suit that's going to be this royal flush. And once you know that, you need to get 5 cards in your hand, and you have to. There are only 5 cards to pick from: ace, king, queen, jack, and 10, and you have to take all 5 of those cards. And what this works out to be is 4 times 1. Is there are only 4 possible royal flushes, which, if you play poker, that I hope makes sense. There were 4 of a kind. This is how I like to think of 4 of a kind. That means I need 4 of any one, all of one denomination, and then any of the remaining cards. So I think there are 13 different values of cards or denominations you can pick from, and you need to pick one of them to be your 4 of a kind. Once you've done that, we're going to need to choose how many of that denomination you're going to get. There are 4 cards in that denomination, and you need all 4 of them. So this is choosing the value to be your 4 of a kind. There's still 1 card to pick from. We still need to choose 1 card, and there should be 48 other cards left in this deck that you could choose to be your 4 of a kind. So this is the other card. And when you multiply this together, you get the number of 4 of a kinds, which ends up being 13 times 48. Lastly, if we're going to get 2 pairs that are distinct, so not 2 pairs to make 4 of a kind, but 2 different pairs of cards, this is how I think of it. I know that I need to pick the 2 denominations to be the 2 different pairs, and it doesn't matter which order I pick them. Like if I do 2s, then 10s, that's the same as 10s and 2s. So I have 13 denominations of cards to pick from, and I need to pick any 2 of them to be my 2 pairs. Once I've gotten those 2 things picked, then of the 4 cards in the first denomination, I need to pick 2 of them. Of the 4 cards in the second denomination, I need to pick another 2 of them. So here represents all the ways to get 2 pairs. There's still 1 more card in my 5-card poker hand that I need. And what cards can I choose from to be that final card? Well, it can't be any of the 4 cards in the first. Otherwise, I'd have 3 of a kind, not a pair. It can't be any of the 4 cards in the second denomination. Otherwise, I'd again have 3 of a kind of that and not a pair. So I think there's 52. Take away 4. Take away another 4, which leaves me with 44 cards that I could possibly pick from. And multiply all this together, and this will give me an expression for the final, for the number of hands with 2 pairs. If, again, playing 5 cards dealt and playing weirdly alone.